Good afternoon, everyone. Today we're doing section 5.4.2. We're still working with sum and difference identities, but this time we're going to be using them to verify. So it's a little bit easier because they actually give us what it's going to equal in the end. We just have to verify that it's true. So we just need to show the work to prove what identity they've given us is true. Alright, so this one is asking us to verify that the sine of pi over 2 minus x is equivalent to just the cosine of x. So since we're subtracting two quantities inside our sine function, we're going to be using our difference identity. And so I've copied a mini cheat sheet of our identities right here. So just to make sure that we label this correctly, I'm going to go ahead and say that alpha is always our first term inside here, so that's going to be pi over 2. And beta, which is our second one, is going to be x. Notice it's not negative x because my difference identity already assumes that we're subtracting, so we don't need to include the negative in our beta. So alpha is pi over 2, beta is x. Now I can go ahead and plug into the difference identity for sine. The difference identity for sine says that it's sine of alpha times the cosine of beta minus, sine keeps the same sign, cosine of alpha times the sine of beta. And we're trying to prove that that equals just the cosine of x. So when we do replacement, alpha is pi over 2, so this is the sine of pi over 2, times the cosine of beta, that's the cosine of x, minus the cosine of alpha, that's the cosine of pi over 2, times the sine of beta, which is just the sine of x. Okay, and we're just trying to prove that this is equal to the cosine of x. So now we can use our unit circle to evaluate the sine of this function. We're going to have to leave cosine of x in terms of cosine of x because we can't actually evaluate that. But the sine of pi over 2 is equal to 1, so this changes to a 1 times the cosine of x minus, and cosine of pi over 2, that's going to change to a 0. So this is 0 times sine x. And so on a lot of these cofunction identities, you're going to notice that you get a 0 or something that cancels out. So 0 times sine just goes away. That turns into a 0. And so we're left with 1 times cosine minus 0 is just cosine of x. And it does indeed equal the cosine of x. And so we verified the identity. Okay, pretty simple. This should be a familiar identity. This is one of our cofunction identities, right? It says that the sine of an angle is equal to its complementary angle. So 90 degrees minus x is the same thing as the cosine of x. Okay, let's go ahead and try these two. Okay, here are the solutions to the guided practices. This one is very similar to the one we just did. They just reversed it and wanted to see if you could prove it using cosine and showing that it's equal to sine. This one was a little bit tricky only because they gave you reciprocals, so you had to write them as 1 over sine and 1 over cosine. But once you realize that you're just trying to get the two denominators to be equal, it was pretty much the same as the first problem we did. So hopefully those didn't give you too much trouble. We have one other example to work on today, and that's verifying a reduction identity. And a reduction identity is very similar to a cofunction identity. It just doesn't always involve 90 degrees. We used pi over 2 or 90 degrees in our previous problems. These could use any of our quadrantal angles. So let's go ahead and verify each of these now, still using our sum and difference identities. In fact, let me go grab my little cheat sheet here, copy that and bring it over. There we are. So this is a sum identity right here, sine of theta plus 3 pi over 2. So I'm going to identify theta as my alpha. It's my first angle. And beta is going to be 3 pi over 2. And we're trying to prove that when we use the sum identity on this side that we get it to be equal to negative cosine of theta. So sine of alpha would just be sine of theta times the cosine of beta would just be the cosine of 3 pi over 2 plus the cosine of alpha, which is the cosine of theta, times the sine of 3 pi over 2. So we're going to evaluate the ones that we can cosine of 3 pi over 2 is equal to 0, so this becomes a 0, times sine of theta, plus the sine of 3 pi over 2, that's equal to negative 1. So this is negative 1 times cosine theta. And sure enough, the 0 times the sine theta cancels out, that's nothing. And we're just left with the cosine of theta times negative 1, which is just negative cosine theta. And so we've proven or verified the reduction identity. Okay. Let's try the same thing similarly with tangent. This is a difference identity. We'll go ahead and label alpha and beta first. Alpha is going to equal x. Beta is going to equal 180 degrees. And we're trying to verify that this will reduce to just tangent of x. So looking at my difference identities, I've got to do the tangent of alpha, so that's the tangent of x, minus the tangent of beta, that's minus the tangent of 180 degrees. And all of that is divided by 1 minus tangent, or sorry, 1 plus tangent alpha. Alpha was x, and tangent of beta, beta was 180 degrees. So we can replace tangent of 180 degrees. If you look on your unit circle, tangent of 180 degrees is 0. So those are going to change to zeros. So we get tangent of x in the top minus 0, divided by 1 plus tangent times 0, that will cancel in the bottom. And we're left with tangent of x over 1, which is just tangent of x. So it is verified. Okay. So mostly this is an exercise in just plugging into your sum and difference identities and making sure that you understand how the reduction and cofunction identities work. Okay. If you want to try 2 of those on your own, here are 2 examples. I'll put up the answers in just a second. So there are your solutions. Again, each of these are just verifying cofunction identities that we already know to be true. So it should work out pretty easily. Just be careful about the order that you put alpha and beta in, and that you actually are applying the sum and difference identity correctly. Okay, that's it for today. Have a great night.